Hello again, this is Mr. V. Hill. Today we're going to be talking about two variable inequalities as well as systems of inequalities. And we're just going to look at a couple of examples here. The first one is this inequality here, y is less than 2x minus 4. Now notice we have two variables in here, an x and a y, which means that we're talking about a two-dimensional space, meaning the coordinate plane. So what we want is to know all points x and y, x coordinate and y coordinate, that will make this statement true. And so all we have to do is just graph this thing. And let me show you how we're going to do that. First, what we want to look at is where equality would happen. Now we're not going to include those points where equality happens because we have a strict inequality here. Just y is going to be less than this, not where y is less than or equal to. But the boundary for this set is going to be where equality happens, and that's going to be a line. This is written in kind of slope-intercept form, except that we have an inequality here instead of the equal sign. So first we need to know where equality happens, and that's just, we imagine that this is an equal sign and we graph that line. So if this were an equal sign, we would have a y-intercept of -4 and a slope of 2. That's easy enough to do. So here is our y-intercept of -4. Right there, and then we follow our slope of 2, meaning a rise of 2, a run of 1. There's another point on the line. We could even go again, rise of 2, run of 1. Here's another point. We could get a bunch of those if we wanted to. And so the line, and then we would play connect the dots to get the line where equality happens. Now, since we have a strict inequality, we need to show that we don't actually want the points on the line. The way we're going to do that is with a dotted line. Okay, so there's a line where equality happens. I show that I don't want those points by using a dotted line. It's just like using an open circle in the one variable case. So if we include the boundary, we use a solid line, and that is for things like less than or equal to or greater than or equal to. And if we want to not include the boundary, we will use a dotted line. That's for a strictly less than or strictly greater than. Okay, so here's our boundary. We don't want to include it, but we want all points where the y's are going to be strictly less than that. So for a given x, say this one, equality happens here on the line. So we want the y's to be less than that. Now, y's go up and down. Bigger y's are going up, smaller y's are going down. So instead of just using the line, we want every point that's below the line, because that's where the y's are going to be less than. So, and we show that we want all of those points just by shading in one side of the line. So everything on this side is, when we take the point here and we plug the x coordinate in here and the y coordinate in here, we're going to get a true statement. That's the basics of two variable inequalities. And this has a name. It's a half plane, this particular set, because, well, we're splitting the plane in half with the line and we're just using 1/2 of it. So that's called a half plane. So that's how to graph a two variable inequality. Now, there's no reason to only graph one at a time here. So we can also have systems of inequalities. And so it's really easy to graph these two. We just have more than one half plane graphed on the same set of axes. And here it's kind of helpful to have two perhaps differently colored pencils. So we can do this one in, say, blue, and we'll do this one right here in perhaps red. And then the points that are going to satisfy both this inequality and this inequality will be shaded both blue and red, meaning it'll be purple. Hey, color, it's great. So anyways, let's just graph these really quick. And it's not too hard, again. The first one, which we're going to color in blue, y is greater than or equal to 1/2 x. Nice, this is in slope-intercept form essentially. Our y-intercept is 0, our slope is 1/2. So it's easy enough to graph. Here's our y-intercept at the origin. Then we rise 1, run 2 to another point. Maybe do it a couple of times. We can even go back the other way. Now notice this is a greater than or equal to, meaning we're going to include the boundary. We do want the points that are on the line, so we're going to show that with a solid line. And so every point on that line, that's where equality is going to happen. We do want those points, so it's a solid line. Now we want the y's to be greater than that. So bigger y's are to the top, so we're going to shade everything above the line. And so every point up here in this half plane, to include the boundary, the line, if we plug the coordinates in, x coordinate here, y coordinate here, we're going to get a true statement out. Okay, now we need the second inequality. Oops, this one is in standard form, so we can't just use our y-intercept and slope to graph the line. We're going to have to use the intercepts, which are really easy to find. So first, the x-intercept is going to happen when the y is 0. So all we do is we cover that up, because if y is 0, 2 times 0 is 0. That just goes away. And so 3 times x has to equal -6. We're imagining this to be an equal sign to get the boundary here. So that means the x-intercept, is going to be -2. Right here. And then the y-intercept, well, the y-intercept is going to occur when x is 0. So the y value that's going to make this statement true, -2x is equal to -6. That's going to be a +3. So there's our y-intercept for the boundary line where equality would happen. But we don't want to include the points on that line because we have a strictly greater than, so we'll use a dotted line to represent that. So there's the boundary for the second inequality. But now we don't have y by itself, saying that, oh, the y's are going to be bigger than, meaning shading up, or the y's are less than, shading down, because we have 3x minus 2y over here. So, I mean, we could solve this inequality for y and then have that tell us, or we just test a point. And usually an easy point to test would be the origin. 0, 0 is really easy to work with. Because guess what? We plug in 0 for x and 0 for y. 3 times 0 is 0, minus 2 times 0 is 0. 0 is greater than, strictly greater than -6. Okay. So we test the point 0, 0 in here. 3 times 0 minus 2 times 0. Is that actually greater than -6? Well, that's all 0. 0 is definitely greater than -6. So yes, this point works. Meaning that every point on this side of the boundary line is going to work. No points over here. If this hadn't worked, if this given us something ridiculous, like 0 is greater than 52, then we shade to the other side. Okay. But this point works, so we're going to shade everything to this side of the line. And so the solution set to this system of inequalities is going to be the things that are shaded both red and blue, meaning every point in this sort of angled region here, because these are shaded both red and blue. So every point in this region right here is going to make this system of inequalities true. And now we would not include the points on this particular array here, but we would include the points on this one, because these are both shaded, both red and blue. These ones are only shaded blue. They're not actually shaded red because we have a dotted line here. And that's how to graph a system of inequalities. And so I'm going to leave you with a practice problem. Go do this right now.